Hey guys, doing a quick video on Prim's algorithm. Basically, the purpose of Prim's is to find a minimum spanning tree in a given graph. And Prim's algorithm works a lot like Dijkstra's. We're basically going to start at a vertex, and we're going to look out from that vertex at the different edges and the different vertices we can travel to. And we're going to keep track of the shortest possible way to get to every given vertices. The difference between Prim's and Dijkstra's is we're not actually adding up the costs of the distance as we go on. We're just going to look at the actual edge weights themselves. So anyway, let's just do one real quick. So we're going to start at vertex A, and we can see from A that we can either go to B, to E, or to D. And we're going to update our table. First thing, we're going to mark A as known. As you can see, I have on my table already. The distance to A is 0 because we started there, and there was no previous vertex. We didn't come from anywhere. We started at A, so that's just going to be left blank. But we can see that we can go to B, and we're going to mark that distance as 3 because that's the weight of the edge that leads to B. We can go to D, and the distance to that is 4. And we can go to E, which also has a weight of 4 on that edge. And we're going to say, for now, that all of these nodes were visited from A. So right now, the shortest path to all of these nodes that we know of is from A. So we're going to choose the smallest distance value on our table for any of the nodes that are marked false for known. And there's a difference. Just because we know the weight to go to a vertex doesn't mean that that vertex is known. What we consider a vertex being known is when we actually visit it. So as we can see from the value on our distance table right now, 3 is going to be the smallest number on a vertex still marked false under known. So we're going to visit B. We're going to change its known value to true. And we're going to look from B. We're going to say, okay, where can we get to? And by the way, we're just going to cross off A here because we never want to visit a node more than once. So we'll just keep track of that way. So from B, we can go to C, we can go to F, or we can go to E. Now in the case of E, we've already visited, or excuse me, we haven't visited, but we've already know of a way to get to E directly from A. But if you'll notice, the edge weight of the edge going from B to E is actually less than it is from A to E. In this instance, we replace the value on our table because remember, we want the shortest possible paths to each vertex. So we're going to replace the 4 under E with a 2, and we're going to replace the previous vertex column as being from B. We're also going to see C for the first time. The cost of that edge we can see is 10. So we're going to fill that in, and we're going to mark that we came from B. We can also see F with a cost of 3 to get there. And so we're going to mark F now. Distance of 3. We came from B. All right, so now once more we're going to look at our distance column, and we're going to pick the smallest value of a still unvisited vertex. And right now that would be E with the value of 2. So we're going to visit E. We're going to change its Boolean known to true. And we're going to look over from E, and we're going to see where we can get to. Well, we don't care about going to A or B because we can see that they're crossed off on our graph. So otherwise, we're going to look at going to F. 11 is actually a larger value than the current value in the table for F, so we're not going to update our table. We can go to D. Same thing here. 5 is larger than 4, so we're not going to update our table. We're seeing I for the first time, so we're going to update our log now, and we're going to say we can get to I with a weight cost of 1. And we're going to mark that we came from E. And lastly, we can get to H for the first time. So we're going to mark on our table that we can get to H with a cost of 2. And we came from E. Okay. Now, once again, we're going to look at our distances. and we're going to look for the smallest value, and the smallest value right now is I with 1. So we're going to go visit I. So let's mark I as having been visited, true. And now that we're at I, we're going to look out and we're going to see. We don't care about the edge leading to E because E has been crossed off. We can get to F with a cost of 3, and we can see that that is equal to the cost on the table already. So we're not actually going to change the table in that case. Well, we can see we can get to H, but 4 is greater than 2, which is the current cost on the table, so we're not going to update H. And we can see we can get to J for the first time. So we're actually going to fill in the table that J can be visited for a cost of 7, and we'd be coming from I. And just a quick note too, the distances usually on these tables sometimes are marked all as infinity until you fill them in. I left it blank at the start, so if you see that, that's infinity is just what represents, well, we don't know where it is yet. So sometimes you'll see a chart and it'll be totally filled with the infinity symbol, and that's really all that means. It fills in as you go. So now, once again, we are going to look at our table, and we're going to choose the smallest value that is still not marked true. And at this point, that's going to be H. So we're going to cross off I because we've now visited I. And we're going to travel on over to H. So let's mark that as true. And let's see, where can we get to from H? Well, the only vertex that we haven't seen yet that we can get to, or excuse me, that isn't crossed off yet, is D. With a value of 6 leading over to D. 6 is larger than the current value on the table for D, so we're going to ignore that. We're going to cross off H, because there's really not much we can do from there. Then once again, we're going to look at our table, and we're going to say what's the lowest value. Well, at this point, it looks like 3 over at F is going to be our lowest value. So let's mark F as being visited. And we're going to see where can we go from F. We can go to C. 6 is smaller than the lowest than our current table on the value. Current value on the table. Bear with me, guys. So we are going to change C to 6. And we're going to mark that we are coming from F. Now we are going to also see G for the first time. So we're going to fill in G, coming from F with a cost of 2. We see we can go to J, but the cost for J currently is actually lower than what's on this edge, so we're going to skip it. And now once again, we're going to look at our table. We're almost done. And we are going to see, it looks like G is going to be our new lowest. So we're going to mark G as being visited. True. And we're going to see where can we get to from G. This is going to be our new lowest cost for C. And we don't care about J because it's not lower than what we already have on our table. So we're going to update C coming from G. And we're going to update the cost to get there as being 1. Now once again, we're going to look at our table. And we're going to see that 1 there for C. We're going to choose C. So mark that as true for known. So from C, there's nowhere new we can go. So we're done with that. Gonna once again go to the table. We're gonna see D with 4. We're gonna mark that true. We're gonna look at D And we're gonna notice there's nowhere we can visit that we haven't visited, so we're done with that. Then we're gonna come back to J, mark that true. We're gonna look at J, and again, every other node has been visited, so we are now finished. Okay guys, so what we can do here in order to figure out what this table actually corresponds to, what minimum spanning tree, is we can look at the right side, okay? This PV is the previous vertex. And what that means is, so in this case, A goes to B. So we can take A and draw an edge to B. Then go down to the next column, or excuse me, row. G is going to go to C. A is going to go to D. B is going to go to E. B is going to go to F. F is going to go to G. E is going to go to H. E is going to go to I. And finally, I is going to go to J. Now you can see that this is in fact a minimum spanning tree. There is no cycles, every node is connected, and that is how you perform Prim's algorithm.